Okay, this is the second part of the lecture on binomial random variable and distribution of binomial random variable. And I'm assuming at this point you know the meaning of the formula which we use to calculate probabilities of binomial random variable, the probability masses. So the formula states like that: if dx, the random variable, is binomial, which is this notation, binomial, and you have two important parameters to know about. The first one is the number of trials, and the second parameter is the probability of success on any given trial. So is how you calculate the probability that x is some particular number, like 2, 3, or whatever. Now I'm calling that in general k, right? So the formula says what you need to do is you need to calculate this n chooses k. This is a coefficient, but you could just write c n chooses k. So that's the first number you need to calculate. The second number you need to calculate, the factor you need to calculate, is the power. The power is made out of the base of the power is p, probability of success on any given trial. The exponent of the power is the number of successes. And the second and the third factor, actually, so I have 1, 2, 3. The third factor is another power. You have the q as a base of the power, which is the probability of a failure, and then on the top you have the exponent, which is number of failures. N is the number of trials, k is the number of successes. When you subtract the successes from the number of trials, you get the number of failures. Okay, so that's the formula. How to calculate, again, probability that x is going to be particular number, k, number of successes, k. Okay, so once you know this formula, you can calculate any binomial probability. You definitely need to have you definitely need to have the ability to calculate something with the probably scientific calculator, or you're going to end up by doing lots of calculation with the powers, right? The power could be quite large powers. So, okay. You also need to identify the random variable to be binomial. If the random variable is not binomial, you cannot use this. So this is the formula only to calculate probability masses. So this is on the left side, and on the right side is the same thing, probability mass of a binomial random variable. So to be able to calculate that, you have to have binomial random variable. The x must be binomial random variable. So I'm going to start with the example number 4 in this story of calculations, how to use it. It says this example: according to some statistics, 1 out of every 4 convicted felon, the people that are released but they have been convicted for felonies, are going to reoffend again. Okay, it's like 25% of them will reoffend again, 75% won't. Okay, a state prison releases 6 convicted felons today. Like again, 75% won't. Okay, a state prison releases 6 convicted felons today. Like I'm making up example, right? What is the chance that none of them will reoffend again? Now, you don't really need to know binomial random variable. You can actually answer that by simply using properties of probability. What that will be: the first will not reoffend, the second will not reoffend, the third will not reoffend, the fourth, the fifth, and the sixth will not reoffend. And now you have the separate probabilities. This is independent. The people are independent. So you can just, this is independent, simply multiply. But you can use binomial random variable. Okay, so what is the story here that we have as a binomial random variable? Okay, x, the number of reoffenses, is what we are going to calculate as the number of successes, right? So again, the success and failure, we have no ethical values here about it. It's just something had to be success, something had to be failure. So reoffense is a success. You have 6 trials. You have fixed number of trials. So you have to go to this list. What is binomial random variable? So the trial is repeated fixed number of times. Yeah, 6 times, 6 guys. Which one of them will reoffend or not? Okay? Each trial is independent of any other trial. Yeah, that's an assumption that you always have to have if you don't have any better information. So each of those convicted felons are going their own ways, and they're not, if one reoffend, the other one does not necessarily have any impact of the first one, right? That should be assumption. Now, if you know that two of them are brothers and maybe they are going to the same household, that's a different story. But we don't have that information. So the independence is assumed if you don't have any better information. So you have the first two. All trials are performed under identical circumstances. Yes, again, you don't have any better information. So you have to assume that the first person is likely to reoffend with a 25% chance, because that's the population information we get. The quarter of the people that are released as convicted felons are going to reoffend, right? So that we have to assume. So we have to assume that it's identical circumstances in each case. Of course, if you have better information, it's a different story, but we don't have that. And then there are two outcomes of each trial, success and failure. In this particular case, that's an offense, a reoffense, or not. So we have all four conditions that are needed to have the number of successes, number of reoffenses declared binomial random variable. So that's the first step you have. Now you have, I declare the number of reoffenses again, the count of those that will reoffend. So the people that will reoffend, I should be more precise, right? Because one person could reoffend 3 times, but then the people that will reoffend, the count of those that will reoffend is the binomial random variable. And that is going to be binomial random variable. So the x is binomial random variable. X is binomial random variable. Given trial is 25%. The chance the person will reoffend is 25%. 1 out of 4. You can write that. And the excuse me. I need to write n first, right? So the first I need to write n. How many trials we have? We have 6. And then I need to write the p. What is the probability of success on any given trial? And I already said that's 0.25, 25%, right? In any calculation, when you use percentages, you always use decimal numbers. Okay, so this is our random variable. Okay, so the first question is, what's the chance that nobody will reoffend? That's the math lingo, how to write it down. Probability that our x is 0. Number of people that will reoffend will be 0. And I just simply use the formula. Look at that. So n chooses nobody's going to reoffend. The k is 0. Okay, n chooses 0. Probability of success 0.25, power of 0. Probability of failure 0.75, right? Failure and success are complementary probability. One is 25%, then the other one is 75%. And the failures, people that will not reoffend, 6 of them, is the power here, right? N minus k. K is 0, n is 6. 6 minus 0 is 6. Okay, when you calculate that, this, by the way, is just 1. There is only one way you can choose nobody from the group of 6. You choose nobody, right? That's kind of clear. But if you just simply calculate this by using your calculator, it's 1. This is 1. This is also 1. 0 power of any number other than 0 is always 1. And you just basically have to make a 6th power of 3/4 or 75%. And it turns out to be, you can use your calculator to do that, it turns out to be 18%. Okay. Question here, what is the chance that 3 will reoffend again? Again, you have the probability mass, probability that x is going to be 3. Right? Again, the same formula. N chooses k. Now the k is 3 here. N is 6. 6 chooses 3. Okay, this is going to be some number to calculate. And we have 3 successes. Probability of success. So again, how many successes? What's the probability of success? How many failures? What's the probability of failure? Those are 2 powers, right? 3 successes. Probability of success or reoffense is 25%. 3 failures, 75%. 3 will reoffend, 3 will not. What's the chance of that? It turns out to be 13%. Okay, you can certainly use a calculator to do that. So I have 6 chooses 3. Okay, you can certainly use a calculator to do that. So I have 6 chooses 3, 6, math, combinations, chooses 3, 20. You can also calculate it yourself, right? Time, now I have a 0.25 with a power of, I use hat here for power, right? With a power of 3. I have to move the arrow so I can get, I have to multiply that again with the 0.75. One more time I'm using hat here to get another power 3 cube. And I have that. So this is 20 times the cube of 0.25 and cube of 0.75. And the answer is 0.131835. In short, 13% if you're looking for the nearest percent. Okay, you can do it that way. Okay, the third one is a little more complicated. It says no more than 2 will reoffend again. What does that mean? No more than 2. Well, that means 0, 1, or 2. Right? Those are separate events. Mutually exclusive, I should say. Right? That means if you calculate the probability each one of them separately, you just need to add 0, or it's going to be 1 reoffending, or it's going to be 2. Right? Those are different mutually exclusive events. We already calculated for 0. That was the A part of the problem. So that was 18%. Now we have to calculate for 1. I'm using exactly the same formula. 6 chooses 1, 0.25. Successes, probability of failure, number of failures. So that's for 1. And this is again for 2. Okay, 6 chooses 2. The number of trials chooses the number of successes. Probability of success 2. Probability of failure 4. That's it. And when you calculate all of that, it turns out to be 83%. Now I'll show you the shortcut how to use it on your calculator. So for example, this third one. This is a probability of having 2 of the people reoffending again. You can do that by using the distribution on your calculator. So second variable distribution. So I need to select second variable and I have distribution. We have lots of distributions here. And the one that you're looking for is the binomial PDF. Binomial PDF is the probability density function. It will calculate the mass. Now how does that work? Well, you select it. How many trials? What is the probability of success on a given trial? We already said 0.25. What is the x value you're interested in? What is that k value, x value that you're interested in? I'm interested in this particular case, 2 successes. So that's number 2. That's it. And I have to, it will pass the instruction for you. If some of you have an older calculator, you might not have a menu. So you're going to have to write exactly what you see here. And then close parentheses. So I don't have to do that. It just did it for me. So that's 6, comma. This is a comma. Doesn't look that way, but it's comma. 0.25, comma, 2. That's it. So I'm getting approximately 30%. So it's 30%. This one is 18%, it's 48%. This one is going to be something else. It all adds up to 83%. So I can calculate the other one. I can just simply use the repeat of the entry. So that's a second entry. You see, it just repeats the previous instruction. And I'm just going to change this one to 1. So that would be if I calculate this middle term here. 1 success. And I just press enter. And so I'm getting here 36%. So I have 36%. All right, 36%, 30%. And this first one was in the A part, 18%. 18% plus 36% plus 30% is 83%. Okay, you might want to be a little more precise in the calculation to get a little more decimals in the beginning until you get every one of them separately, and then you can add it up and then you can round at the end. Okay? Next one. At least 3 of them will reoffend again. That means 3 or more, right? 3, 4, 5, or 6. Okay? That is at least 3. Probability that the reoffenses, the x is the count of reoffenses, binomial random variable, is at least 3, bigger or equal than 3. And I said it in the class once that in the real language we don't use greater than or equal. We just say no less or at least, right? No less than 3 or at least 3. That means greater than or equal. Okay, so that's what we're looking for. Okay, now you say, oh, now I have to calculate lots of stuff. 3 and 4 and 5 and 6, 4 different probability. No, actually you don't have to, because you have already calculated the complementary probability. Look at this. Less than 3, right? This is no more than 2. And this is no less than 3. So those are complementary. This one includes 0, 1, and 2. This one includes 3, 4, 5, and 6. These two probabilities are complementary. So if the first one is 83%, the second one is 17%. That's it. So you have to notice that. You are using properties of probabilities, and they are still in force. Okay? Example number 5. According to some stats, 1 out of 3 males have been cheating on his spouse. I have 5 friends that are married. What is the chance? One of them has been cheating, and at least one of them has been cheating, no more than 1, and less than 3. All right. I'm gonna leave this one, and this one for your entertainment. So like a extra homework that you don't get any credit for. It's not due. So if you don't want to calculate, it's fine with me. And I'm gonna do the first one. One of them being cheating. Okay, let's identify the random variable. X is the number of cheaters. That is going to be binomial random variable because we have 5 of them, or the number of trials is 5, and any one of them could be a cheater, and that will be, in general case, 1 out of 3. So that's our binomial random variable. You can say, well, you didn't verify the conditions. Okay, let's verify the conditions. The first one says the trial has to be repeated a fixed number of times. Yeah, 5. 5 people. Each trial is independent of any other trial. Of course, I have to assume that, because if you don't have better information, that is the general assumption. Now, if you say, okay, 2 of them are related or stuff like that, so if one goes to bar and cheats and another one might be more likely, but that's the assumption, right? So you're making hypothesis, speculation, I should say, not scientific decision to assume something, right? So if you don't have that, you should assume independence. All the trials are performed under identical circumstances. Again, they might not be the case. One person might be much older, so it's less likely to cheat. Somebody might be much younger, more likely. Somebody is moral, somebody is less moral, and so on. But in that case, you really need to know what's the story. You cannot assume that unless you have that information. So you have to assume identical circumstances. There are 2 outcomes from each trial: success and failure. Yeah, cheating or not cheating. Success is going to be cheating, a cheater, and failure will be when it's not cheater. Okay, again, because I'm interested in how many of them are cheating, so I'm interested in number of successes, and that should be cheating, right? So again, the, successes and failure is not an ethical notion. It's just simply, one of the two. You can, if you don't like to call it success and failure, you can call it 0 and 1, or 1 and 0, right? Or A and B, if you like. But this is going to be standard notion that is used throughout statistics. Okay, so again, one of them has been cheating. So we identified that number of cheaters is binomial random variable, with the number of trials being 5 people, and the probability of success cheating on any given trial is 1/3. Okay, what is the, so we were asking, what is the probability that X is equal 1? Okay, and now again you can use the formula, and the formula says you have 5 chooses 1, right? N chooses K, this is K. N chooses K, this is N. Probability of success, cheating 1 out of 3. Number of successes is 1. We're interested in 1 success. Probability of failure 2 out of 3. The number of failures, the one that are not cheating, 4. Okay, when you calculate this, the 5 chooses 1 is in how many ways 5 objects can choose one. And 5 is. Nothing special about it. So you don't really need the calculator to know that this is 5. This is 1/3, of course. And this is going to be a 4th power 1/3. So 4 power 2 is 16. 4 power 3 is 81. So you can calculate it manually, but you can also use your calculator. I'm ending up with approximately 33%. And again, you can just simply check with your calculator. And I am going to check that by using binomial probability, right? So I'm going at second variable, give me distribution. I'm going to the binomial PDF. So if you don't want to calculate all of that, it's to be done separately, right? And then multiply. This number of trials, this time I have 5. I have probability of success on a given trial is 1 divided by 3. So you can just write like that. Your calculator will calculate that further. The x, the value I'm interested in, is 1. 1. Okay. Move the arrow and paste. And now it just does that as an instruction. Binomial probability density function, PDF, that's how it's written. Parenthesis 5, comma, 1/3, comma, 1, close parenthesis. If you don't have a menu, that's what you're going to have to write. And you have 33%. That's, so I figured out this is actually ought to be wiggle. Wiggle here, because it's not exactly 32.92, 32.92%. It's a little more decimals. Okay. I'm going to leave B, C, and D for you. And I'm going to do something similar here. Example number 6. 1 out of 4 women that are smoking will die from smoking-related diseases. In my workplace, there are 8 women smokers. What is the chance that more than 2 will die from smoking-related diseases? B. More than 2, but less than 5. This is a kind of interesting question. I'm going to calculate this one here. And I'm also going to do this one. All right. So let's see. More than 2. So that will be 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. So you can say, wow, now I have to calculate 8 separate probabilities. Or what did I say? 6, not 8. 6 separate probabilities. That's a long calculation, right? First of all, you need to identify that you have the number of ladies that are going to die from smoking-related diseases, a binomial random variable. You should go to that list of 1 to 4, make sure that's the case. Success is dying from smoking-related disease. X is binomial random variable. We have the count of trials is how many? 8. That's n, the number of. I'm going to use complementary probability is less to calculate. What's a complementary probability? Less than 2 or equal to 1 and 2. Right? So if you have in here, in this probability, in this event, you have a 3, 4, 5, 6, 7, or 8, the complementary would be 0, 1, and 2. So if I calculate complementary, I just have to subtract it from 1, because that's the rule about complementary probability. Whatever I got for complementary, I subtract from 1, and I get from the probability I'm asking for. So the complementary probability is, I said, 0, 1, and 2. And how do you write that? You write that no more than 2, which is, no more than 2 is this, right? No more than 2. We agree? Well, you didn't really agree, but I told you. That is no more, read this. Okay, so that would be 0, 1, and 2, no more than 2, right? So this is much easier to calculate. You can calculate here 0, 1, and 2 separately, and then you add it as 3 probability versus 6 that you need to calculate here, and then you subtract from 1. But I know what is better. You can actually use your calculator for this as a single calculation. Your calculator can do it. Okay, what your calculator does. Okay, so notice here, in the previous calculation I have binomial PDF, which is probability density function, which is a must. I now need a cumulative function, something that accumulates those masses on the way, up to 2, including 2. And there is a function like that on your calculator. Distribution, binomial PDF, binomial CDF. This is a binomial cumulative distribution function. How's that working? Well, you just have to put again, what are the number of trials? I have, 8 ladies, 8 trials. What's the probability of success on any given trial? 1 out of 4. So you have that. What is the X value? That means less than 2. Now, once you paste that, this is not probability density function. This is going to be accumulation of all of the masses up to 2, including 2. 32%. That's the probability that more than 2 will die from smoking-related diseases. It's a good news, right? Well, I don't know. Well, 32% is a chance there will be more than 2. 68% chance there will be 0, 1, or 2. Okay. Now, I'm going to just give you a brief idea how to calculate this. More than 2 but less than 5. There will be 3 and 4. You can do it that way. But I'm going to show you that this is how you calculate this by using a calculator. So you can calculate separately yourself. 3 and 4, that's it. More than 2, less than 5, that's 3 or 4. 3 or 4. 3 probability for 4. And mass, probability mass at 3, probability mass at 4, add it up, that's what you're looking for. But you can also calculate that by calculating the probability up to 5, up to 4. Which you can use your calculator. And you can calculate probability up to 2. So again, you have on your calculator. Each one of them is CDF. So I got CDF here for 2, CDF for accumulation for 4. Okay? So when you subtract this, you're going to get 3 and 4. Because this one will be in calculating the probability at 0, probability at 1, and probability at 2. This one will be calculating probability at 0, at 1, at 2, at 3, and 4. So when you subtract the probability that will be at 0, 1, and 2 from a probability that will be at 0, 1, 2, 3, and 4, you're going to get the probability that will be at 3 or 4. Okay? You can say, look, you just simply calculate probability at 3, probability at 4, either using formula or your calculator PDF. It's fine. Yeah, you can do that too. But this is nice to know, because this could be the story about 80 women, and then there will be more than 20 and less than 50. That would be something to calculate. So it's still lesser or equal than 49 if the number would be 50, and then lesser or equal than 20. And you get all of those probabilities in between, blah, 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 to 49. Okay? So that's a little trick here to know. Okay? How to use your calculator. All right. Like every other random variable, the binomial random variable has its distribution, has its variance, has its mean, and has its standard deviation. So, now you can think about, oh, this is going to be some calculation to get that. No, actually, there are formulas. First of all, the probability mass is easy to calculate. So this was the example about the quizzes that we have in the class. So this was the in the first part of the lecture. Where is that example? Quiz, 4 questions with choices of 5 answers each question. That was the binomial random variable. That is the guy's trying 4 questions, so it's 4 trials, and a chance of 1 out of 5, right? If you have A, B, C, D, and E, 1 out of 5 is a chance of guessing it right. Okay? So, but you're simply using a formula. So use the formula. The chance is going to get 0 guesses is about 41%. Chance is going to get 1 right guess is 41%. The same. Chance of 2 right guesses, 15%. Chance of 3 right guesses, 2.5%, or 2.6% if you like. And chance of all 4 right, it's going to be 16% over 1%, so less than 1% here. Obviously, this must be a distribution table, so this adds up to 1. I'm not going to check that. I know it does. So that's how you get a distribution table. So again, the values around the variable, how many questions he can get right. 0 or 1 or 2 or 3 or 4. And then you calculate the probability for each one of them by just simply using formula. That's it. So that's the distribution. And here's a probability histogram, right? It's a probability histogram. You can get 0 with about 41% chance, 2 with about a little more than 15% chance, 3, well, 2.6% chance, not likely at all, and 4, almost never, 16% over 1%, less than 1%. So this is kind of sliver here, a little. This is a bar, but the height is so low that's not much to see. Okay, now the kick is that we know the expectation by using formula, and we know the variance by using formula. That's amazing. And how is this going to work? Well, you just have to think about it. If he's guessing 4 questions and he's got a chance of 1 out of 5, each one of them to be right. So it's 1 out of 5. It's 20% of the 0.2 out of the first question right. 0.2 out of the second question. It's like a partial credit right. 0.2 out of the third one right. 0.2 out of the fourth one right. And that's it. That's 0.8 total. He's going to get 0.8 right in a long run, right? That's the average number of questions he's going to get right in a long run. What am I doing here? I'm just simply looking at that as a partial credit. So he's not likely going to get a first right, but he's got a chance to get it right. So 1 out of 5, so that's like a 20%. Now if I give him partial credit for a bad guess, there'll be 20% chance. 20% of the first one, 20% of the second one, 20% out of the third one, 20% out of the fourth one. Just basically the number of trials, the number of questions, time probability of success on any given one. Okay? 0.8. In a long run, he's not even get 1 question right per quiz. He can get 0.8 right per quiz. So sometimes he gets something right. Maybe more than 1 sometimes, but not very often. Okay? So the formula is, to get an expectation, you just simply need to multiply the number of trials and the probability of success on a given trial. Now in this case was number of trials 4, P was 0.2. If you multiply that, you get the expectation. Now you can say, oh, how do you know that? Well, you need to calculate it out of the table. Yes, that's true. So I'm just using a kind of common sense here, but that's not good enough. Now, this can be shown that this formula is in general case always the case by using so-called Newton binomial theorem, which we are not going through. So, Sir Isaac Newton knows that this is right because he invented the theorem. So you can check this out theoretically, but that involves lots of algebra, so I'm not going there. Right? We also can calculate variance very easily. Okay, what's the formula for variance? Again, that can be also shown, and I am not going to show that either, but I'm going to show you the formula. The variance is MPQ. It's that simple. So the expectation is MP, the variance is MPQ. If you calculate the expectation, you just simply multiply that one more time with Q, and you're done. So MPQ in our case, that would be, so we have a 4 times P times Q. P is 20%, so Q is complementary probability. Probability of failure is 80%. All right? When you multiply this, you get 4 times 2 is 8. 8 times 8 is 64. Decimals of 2 of them. So 0.64 in this case. So these are the formula. One of them for expectation, the other one for variance. The standard deviation, of course, is going to be the the radical of the variance. So in this case, would be 0.8. Radical of 0.64 is 0.8. You can check that out with your calculator. That's amazing. So the formulas are very simple. You don't need to do the whole table calculation to find out what the variance is, variance. You don't need the table to calculate the mean either. You just simply need to remember this formula. You have to remember the formula. We're going to use that down the road. So the expectation formula is just to multiply n and p. That's it. The variance formula is just multiply n, p, and q. That's it. It's that simple. Very simple formula. Again, this is true. And you can show that not by using common sense, which I try, but by using straightforward algebra. But for that, you need to know something in algebra that we use, something called Newton's binomial formula or Newton's binomial theorem. Isaac Newton, another time that we mentioned him. But then you would know. Okay, there is one special case of binomial random variable that is used very, very, very often. Polling. Okay? When you are polling one person, you're asked for opinion of that person. So for example, nowadays you can ask, you support the policy, some kind of policy, whatever. He's going to say, no, that's 0, failure. Or yes, that's 1. Or do you support that candidate, political candidate? Political polling is done that way. Or something like, marketing. Do you like this color on this brand of cereal? And he's going to say, no, I don't. Or, oh yeah, I like that color, right? So that's again 0 or 1. So this is what you do very often. So what do you have here? Well, we have binomial random variable with one trial only. It's one trial, one person, one trial. Okay? It could end up with the yes, 1, success, or 0, failure. And the P is the proportion of the people that will, if you talk about a political candidate, proportion of the people that support that political candidate. So be on any given trial a chance that will be exactly the probability that this person is going to say, yes, I'm supporting that guy. Okay? This is called this particular random variable. So, random variable, that is a binomial random variable and has only one trial and some kind of probability of success, proportion of the population that would say yes, is called, this is binomial random variable, it's called Bernoulli random variable. It's also called indicator random variable. But more often it's called Bernoulli random variable. You gotta remember this one, okay? Because this one is the most important one, because it's always used in polling, right? You can say, well, you're polling 300 people, not 1. Yeah, but in one case you're polling 1 person. When you're talking to 1 person, you're polling 1 person. 1 person. You can poll that repeatedly, and then you have some sample of binomial random variable repeatedly used. But in 1 person, that's 1 trial. Okay? This is a very important random variable for us because it's used in polling. And it's called Bernoulli random variable. You might wonder why is Bernoulli random variable, not something else. Maybe you could call it single binomial random variable, something like that. Bernoulli by Swiss mathematician Jacob Bernoulli, who lived about 300 something years ago, and he was a good gambler, so he was doing a lot of work about probability and gambling and stuff like that, and of course in mathematics as well. A genius of his time. So he was tackling this kind of situation for polling and games of chance. So to honor him, we gave the name to this random variable, Bernoulli random variable. Apparently he was using it. Okay. Now you also need to remember 2 things about this random variable. The expectation is just p. Why? Because you're multiplying 1 and p. I mean, you're using this formula, 1 times p is just p. Bernoulli random variable has probabilistic expectation, probabilistic mean is just p. And it's also a very simple story about the variance. Again, you're using this formula in general for binomial random variables, so that will be n pq, but in this case n is 1, so it's going to be 1 times pq, or pq. So the p is the expectation and the pq is the variance. You couldn't possibly get simpler formulas than that. But you got to remember that we're going to be using that. Again, this is random variable. That is binomial random variable, but it's only one trial. One trial. Okay? And then we give a special name to this random variable. We call it Bernoulli random variable. And this random variable is used in polling. And polling is very important in applied use of statistics, because polling is done just about anything: marketing, sport, politics, economy. Always there is some polling around, and so you need to know about this random variable. Okay, we're going to go back to that random variable at some point in the future, so you need to remember that. Okay, that's my story for this second part of this lecture, which I was doing mostly the problems. And you can watch this again. I am going to end this stream and the video, and I hope you are going to be doing homework